So we've been studying this line integral here, this line integral with respect to arc length, right? So we're integrating this two-variable function along some curve in the xy plane. And to keep it simple here, I'm just, again, going to restrict myself to talking about two variables. But this, of course, works perfectly well with three variables. Just add a z in with everything. But all right, so we defined this integral like this. But now, what if instead of, for these segments of the curve, instead of keeping track of this delta SI, we switched, let's actually just say switch, delta SI, so instead of keeping track of the change in the length on the curve, we instead just keep track of, well, how does the x value change? Or how does the y value change? Right? Now notice there's a key difference here. This is always positive, right? Because arc length is only going to go up as you travel along a curve. But, well, let's say we have a curve that looks like that for some reason. Then delta x, as you go from here to here, it's going to be positive, but as you go from here to back here, it'll be negative. And then delta y, if you go from here to up here, you're going to be positive, or even this whole time all the way up here, delta yi is positive. But when you start going down, delta yi is negative now, right? Because here we're just concerned about, how is this changing in the x direction, or how is it changing in the y direction? So now, well, what if we did that to the integrals? Well, then we get two new kinds of line integrals. So this is going to be the line integral of f along c with respect to well, now we get to do two different ones here. So we can first do with respect to x. Right? So that's going to be switching this guy for delta xi. So as you might guess, that's just going to produce an integral that we write like this. All right? And how do we compute that? Well, it's really not too bad. Right? Let's actually even go back here real quick and say c is parameterized by r of t, and t goes from a to b. And you know what? Actually, this time, I also want to tell you what r of t looks like. I'm going to just pick a generic r of t, of course, but I want to say this is x of t, y of t, and that t goes from a to b. Because now I can write this integral down like this. Right? But the dx, that just becomes x prime of t dt. All right? And then you can probably guess what the line integral with respect to y will look like. Well, we write down the same thing here, except with a dy now. And then this is the integral from a to b of f of r of t times y prime of t dt. All right? So these are two new types of line integrals we have. We can do a line integral with respect to x or with respect to y. All right? And then, we can actually kind of have these happening together. Right? So say we could have, let's just say we could also have an integral that looks like this. I'm going to say p of x dx plus q of xy dy. We could also have a line integral that looks like that. Right? And then, we just imagine breaking this up over the sum. And so this is just going to be the integral over c of p of xy dx plus the integral over c of, I can't save that into a q, q of xy dy. All right? So you can ask now, well, what are the differences? Why do this? Well, we'll see in the next video. All right. So now let's illustrate some points of these line integrals with respect to, x, y, and z and combinations of them. And let's see sort of what properties these really have. Right? So let's start by doing this integral, part A here. Okay. So this integral here, which let's just start by writing out, plugging in the stuff. So integral from 0 to 2 pi of, well, y dx, so we're plugging in y, so sine of t. Dx is x prime dt, so negative sine dt, negative sine of t dt. Let's clean that up a little bit here. Negative sine of t dt. Okay? Now minus x dy, well, x is cosine t. Dy is y prime dt, so cosine of t dt. Okay? Plus z dz, so plus t, well, dz would be z prime dt, so 1 dt, so just dt. Okay? So this is the integral from 0 to 2 pi of negative sine squared t minus cosine squared t plus t. In other words, integral from 0 to 2 pi of t minus 1. Right? So if we integrate that, we get 1/2 t squared minus t from 0 to 2 pi. And so that just ends up being 2 pi squared minus 2 pi. Okay? So now let's compute the next integral. So b. Let's call this parameterization R2 of t. So we want the line segment from 1, 0, 0 to 1, 0, 2 pi. So, well, 1 and 0 are always staying the same. And 0 to 2 pi, we can just write this as 0 less than or equal to t less than or equal to 2 pi. Right? And have t in the z component there. Right? So again, let's do the same kind of thing. Instead of rewriting all this out, let's just plug this stuff in. So 0 to 2 pi, well, y is 0, so that first thing is 0. So 0 dt from the first one. Okay. X is 1, but dy is y prime dt. Well, y prime is also 0, so plus 0 dt. Right, and then we get t dt again here. All right. So this is just the integral from 0 to 2 pi of t dt, which is 1/2 t squared from 0 to 2 pi, which is 2 pi squared. Well, hopefully you already noticed something interesting here. Right? Remember, so let's look at this. This R1, this path in A, where does it start? Well, if we plug in 0, we get 1, 0, 0. So these two start at the same point in A and B. Where does the curve in A end? Well, if we plug in t equals 2 pi, we get 1, 0, 2 pi. Right? So they start and end at the same point, but the paths are different. And notice that we get different answers in each case. So what that means is it's not only the start and the end that matter for these type of line integrals, but the journey also matters. The curve, the path, it also matters. All right? So now let's do part C and see what happens here. Now notice in particular what part C is it's taking the curve we had in part B and going backwards, right? So what are we doing now? All right. So part C, so we need to come up with the parameterization first. Let's call this one R3. Now again, the x and y components stay 1 and 0 respectively. Now the last component, remember we need it to start at 2 pi and get down to 0. So the easiest way to do that is just 2 pi minus t as t goes from 0 to 2 pi, right? Because then this starts at 0, and then as you get closer to 2 pi, as t gets closer to 2 pi, the z component gets closer to 0, right? Okay, so now let's do this. And again, since x and y are the same as they were up here, we know this is going to start out as 0 dt plus 0 dt. And then now we just have to do the z dz term, which in this case will be 2 pi minus t. And then dz, derivative of this is negative 1. So negative 1 dt. Right, so this all just comes down to the integral from 0 to 2 pi of t minus 2 pi dt. Right, so now let's integrate that. Well, that is 1/2 t squared minus 2 pi t from 0 to 2 pi. So we have here, what do we get? We get 2 pi squared minus 4 pi squared, which is just negative 2 pi squared. So what do you notice here? Notice here that this is the negative of that one, right? So what that means then, not only does the start and end matter, but sort of the direction also matters, right? Because these are both line segments between the same 2 points, but we've traveled them in opposite directions. So what ended up happening is if we go in the opposite direction, we pop out a minus sign. All right? So in the next video, we'll summarize some of these properties and see you there.